तेजस्विनावधीतमस्तु मा विद्विषावहै। ॐ शान्ति शान्ति शान्तिः।
Hello and welcome to yet another session in database management systems. In the previous session we started at looking at a very crucial aspect of DBMS design. Note that I am using the term DBMS design and not database design. We'll look at we'll address this issue in more detail a little later. What is DBMS design versus what is database design? We started by looking into a very crucial aspect of DBMS design, namely that of query processing. We saw that nowadays or in today's world the size of the database is no longer a problem. We can have huge amounts of data stored in very small amounts of space and being available at pretty cheap cost. In fact, I have with me a small device which I can show it for you. This is a small device which is which can hold a database of size 256 megabytes of store, and this costs roughly about 3,000 rupees. So you can store data of the order which was not even envisaged before in very small devices at pretty affordable cost and which occupies very small amount of space. Therefore, storage of data is no longer a problem. The problem today is retrieval of data. Retrieval in the sense it is not just retrieving any data, it is retrieving whatever data that is required by the user. Therefore, we saw the crucial elements today or the crucial technologies of that is going to impact database in the forthcoming years are those techniques that can help in retrieving data elements as quickly as possible from databases. We saw that auxiliary files in the physical storage world, which comprises of index structures and several kinds of hash structures and so on, is one crucial element in making this happen, that is making fast data retrieval happen. The second crucial element is query processing. Given a user's query, can we process the query in such a way as to return the results extremely fast? There are several techniques that are used for making query processing interactive in nature. That is, remember the example of Google. If suppose Google were to say that when you give a web search query, suppose it were to say come back after 2 days for your answer, it becomes unusable. Nobody would use it if there are other alternatives, that is. But a search engine like Google can search petabytes of data, or the search space of data is petabytes of data, and it can return you relevant results within a few seconds. Now this is possible. One of the techniques for this is to use very intelligent query processing techniques. Of course, there are if you throw more hardware into your database, if you throw faster processors, it becomes faster and so on. However, a crucial element is still the algorithm that is used to retrieve data. It can a bad algorithm can make the difference between a database that is very efficient to a database that is unusable for all practical purposes. Let us briefly review what we learnt in the previous session in query processing and move on further today to look at some more aspects of query processing. Efficient query processing is is crucial for good DBMS design. And in fact it can make the difference between a database that is operational or effective and a database that is ineffective. A bad query processor can render a database all but useless when the size of the database grows beyond a certain size, beyond a certain limit. Query processing depends on a variety of factors, unfortunately, and not everything is under the control of the DBMS. We saw yesterday that query processing could depend on, let us say, the memory size, or the size of the tuples, or the size of the relations that are present in the database, and the kind of file system that are stored, whether the file system is fragmented or defragmented and so on. So there are a variety of factors that impact query performance, and not all of these factors are within the purview or within the control of the DBMS. Therefore, query processing is oriented towards obtaining the best out of whatever is available at the behest or at the control of the DBMS. What are the typical steps that are handled or that are executed in a query execution process? Given a query, given an SQL query, the query is first scanned using a lexical analyzer, which in turn returns takes the string which forms a query and returns a set of tokens, and then this token stream is then parsed to build a syntactic tree, or what is called as a parse tree, and then syntax analysis and so on, semantic checks and etc. are all performed, which comprises the validating phase of the query compiler. And once this is done, an intermediate query representation is generated. This intermediate query representation is also termed as a logical query plan tree. Now, this logical query plan tree is usually a tree data structure that represents the relational algebra equivalent of the SQL query. Using this tree data structure, there are several rules that are employed in order to systematically optimize the tree for better performance. The intermediate query representation, or the query tree, is then given to the query optimizer, which generates a query execution plan. The execution plan is also called the physical query plan tree, and in contrast to the logical query plan tree. That means a physical query plan tree comprises of a query plan written in a language that is usually executed by a DBMS interpreter, or would be compiled into machine code for execution. And this physical query plan language comprises of its own constructs, some of which we saw in the previous session, something like table scan constructs and sort scan constructs and iterators and so on, in addition to all relational algebra constructs like select, project, set, union, difference and so on. The query execution plan, if it is an interpreted DBMS, would be executed directly, and the results would be returned to the user. If it is a compiled DBMS engine, the query execution plan is then given to the query code generator, and then appropriate machine code is generated from the execution plan. Of course, the last step would be the code. If it is generated in a compiled mode, it is then given to the operating system runtime or the database runtime, and then query results are given out. Now, we are primarily interested, when we are talking about query processing, in two of these stages in the query execution stages. The first stage that we are interested in is the intermediate form of query representation. In fact, that is something that we have deferred to a later session. We in fact went straight on to the second stage, that is a physical query plan representation. We saw some constructs of the language that is used to describe the physical query execution plan, and constructs that are the physical query execution plan is then either fed through an interpreter for this language which executes the query, or is compiled onto machine code. Now, what are some of the operators that we saw yesterday? The physical query execution plan operators are those set of operators that define the basic physical operations that need to be performed in order to answer a query. These are also sometimes called the internal query operators, or are the operators that make up the internal query language. SQL or relational algebra on the other hand is an external query language, that is it is the query language used by users or application programs that are using the database, but the database itself or the DBMS itself uses an internal language for answering queries that accesses the file system or the storage structure used by the DBMS in order to retrieve tuples in response to a query. This of course comprises of the set of all relational operators plus some additional operators that talk about physical characteristics of retrieval. Some example operators that we saw yesterday was the table scan operator, which can be implemented using an iterator operator, that is an iterator object, so to say, which opens a table and returns tuple by tuple. That is, an iterator, if you remember, has three different functions: an open function, a get next function, and a close function. A table scan operator opens a table when the open function is called and returns the next or the topmost tuple on every get index or get next invocation, and starts incrementing a pointer so that the next tuple is returned, and so on. So the ith get next invocation would return as the ith tuple in the table, and then the close function would close the table. And then there was index scan that would use an index to get a particular or get the required tuple. Then there is the sort scan operator, which not only returns all tuples in a table but also sorts them before returning them. We then saw some set of one pass algorithms that are built on top of this physical query plan constructs or data structures that perform various operations. We divided one pass algorithms into three different kinds of categories. The first category was a tuple at a time algorithm. A tuple at a time algorithm is something like select or project, which needs to concern or which needs to be concerned only with one tuple at any given point in time. Tuple at a time algorithms can easily be executed with a single pass regardless of the size of the relation, because we assume that the tuple is never large enough so that it cannot fit into main memory. We always assume that one tuple of the database can always fit into main memories. Therefore, since we are only concerned with a single tuple at a time, we can always use a single pass algorithm for tuple at a time functions. On the other hand, there are relation at a time algorithms, that is there are functions that need to be concerned with the entire relation rather than each tuples independently. For example, the function called unique in SQL needs to look at the entire relation in its entirety, of course, rather than each individual tuple in isolation. Relation at a time functions can use one pass algorithms only if the relation can fit completely into memory. And it's that's not just that's not enough. In fact, the relation should not only fit completely into memory, but especially for binary relation at a time functions, there should be at least one block left over to read data from the other relation. Hence, if a relation requires m memory buffers, or rather if m memory buffers are present for the DBMS, then the maximum size of one of the relations of the smaller relations can be at most m minus 1. It can't be m, because we need at least one more block for data from the other relations. And of course, that is the limitation of one pass algorithms, in the sense that you can use them only when you know that at least one of the relations can fit completely into memory. Now, how do you know that a relation completely fits into memory? What if you don't know the size of the relation? in such cases you need to estimate the size of whatever data relation or whatever table that you are using. Hence one pass algorithms rely to a very large extent on procuring good estimates of relation sizes in terms of the number of tuples. And if the estimation algorithm is wrong, that is if too many buffers are allocated, that is if the estimation is too high, then there is a possibility of thrashing. On the other hand, if the estimate is too low, then we may not be able to use one pass algorithms at all, because the relation won't fit into memory, and the strategies that we studied for one pass algorithms will no longer be applicable. What do we do in such cases? That is, what do we do in cases where one or both of the relations are too big to fit in memory by itself? For these we use what are called as multi-pass algorithms. In multi-pass algorithms we shall be studying today mainly about two-pass algorithms. Generally many multi-pass algorithms are generalizations over two-pass algorithms, and if we know the general strategy that is used behind two-pass algorithms, it is sufficient, or it would not be too difficult to generalize it to multi-pass algorithms. And multi-pass algorithms, as the slide shows, are used when relations cannot be read into memory in their entirety. Only a part of each relation can be read into memory, and they usually have an alternation between reading part of a relation into memory and writing it back onto disk. That is an alternation between computation and intermediate result generation and retrieval of intermediate results. The first kind of two-pass algorithms that we are going to be looking at are what are called as sorting based two-pass algorithms. We are going to be looking at three different paradigms or three different strategies of two-pass algorithms: sorting, hashing, and indexed based two-pass algorithms. The first one that we are going to be looking at is the simplest, which is called the sorting based two-pass algorithms. The basic idea behind sorting based two-pass algorithms is shown in the slide here. Suppose we are given a relation R. Of course that is that such that the relation R is too big to fit in memory, and of course for the DBMS we are given a maximum of m blocks of memory, that is m blocks of memory elements can be are allocated for the DBMS. Therefore m blocks of data can be read from the relation R by the DBMS at any point in time. The sorting based two-pass algorithms have the following basic structure. This slide shows the basic or the skeletal algorithms for two-pass sorting algorithms. Essentially, as we noted before, the algorithm or any multi-pass algorithm alternates between reading intermediate results and writing them back. That is reading part of data from the disk and performing computations and writing them back. Okay. So the basic idea behind two-pass algorithms are based on sorting is as follows. First start by reading the relations, one or two relations, that is we are going to be concerned only with either unary or binary operators for the time being. In of course any n-ary operators can usually be reduced into one of these forms, and it's a generalization of considering either unary or binary operators. So let us consider that the relation or the pair of relations that we are going to be using are first read blocks by block. Okay. So because we have m blocks that are allocated to us, we can read these relations m blocks at a time. Now m blocks of relations from m blocks of tuples from the relation or pair of relations are read into memory, and then they are sorted. Once they are sorted, they are written back into disk. This is the alternating phase. That is, you read part of data from disk, sort them in this case, which in this case is the computation, and then write them back to disk. Now continue steps 1 and 2 until the relation is exhausted. I am just assuming here that we are dealing with a unary operator, that is until relation R is exhausted, and it can of course mean until the pair of relations is exhausted, or until the set of all relations that are that this query handles are exhausted. And then once these intermediate results are written onto disk, that is sets of different m blocks of sorted tuples are written onto disk, use a variety of query merge techniques. Remember what is a merge technique. If you have taken a course on let us say data structures, you would have come across an algorithm for merging, which is usually seen in relation with sorting. Merging basically means that given 2 or more lists that are sorted, can I obtain a single list that is also sorted, in of course in as efficient a fashion as possible. We have there exist very efficient algorithms for merging, especially when the results are especially when the lists are sorted, that can produce results in a linear order of time. So use a variety of these query merge techniques. Note here that in the 2-pass algorithms, it is no longer just merge techniques, it is query merge techniques. That is, as in when you do the merging, perform your query or answer your query as in when you are doing the merging on these intermediate results. So use a variety of query merge techniques to extract relevant results from all the sorted m blocks on disk. Now let us see some examples of 2-phase or 2-pass sortings or 2-pass sorting based methods for different answering different kinds of queries. And you can notice that all of these examples follow the same skeleton of the basic idea that we presented in the previous slide. So let us first take the example of duplicate elimination. Now as you can see, duplicate elimination is a relation at a time unary operator. We do not have to worry about tuple at a time operators for 2-pass algorithms. Why? Because all tuple at a time operators can be answered using a 1-pass algorithm, because all that we need to be concerned about at any point in time is just a tuple, and each tuple can be checked in isolation with the other tuples. So let us take the first relation at a time unary operator, namely duplicate elimination, that is the unique construct. How do we implement the SQL unique construct? Let us assume that it is relation R on which we have to eliminate duplicates, and of course we have to also assume that relation R is too big to fit in memory. Now as we know that because we are given m blocks of memory available to us, start reading R in terms of m blocks of data, that is read m blocks of data into memory and sort them, and the third step is store the sorted set of m blocks back onto disk. Now continue from step 2, that is read the next m blocks of data from R, sort them and put them back onto disk in a separate file name, let us. Okay. So keep doing this until R is exhausted, that is R becomes empty. Then what is the next phase now? Now we have read a relation, sorted them and put them back into memory, or rather put them back into disk. The next step now is to use one of these so called query merge techniques on these intermediate results that we have generated. So what is the query here? The query here is the elimination of duplicates, that is we do not want any duplicate tuples to appear in the relation once it is output to the output buffer. So how do we eliminate duplicates from this set of sorted intermediate results? So the query merge technique for eliminating duplicates is quite simple. Take one block from each sorted sublist there are several sublists of data that have been generated, and each list of data is a maximum of m blocks in size. That is because we have read data in terms of m blocks, except the last set of data that we wrote. Every other data would or every other intermediate result would be of size m blocks. The last data intermediate element that we wrote would have a maximum size of m blocks. It could also be smaller than m blocks in size. Now take the topmost block from each set of these intermediate results that we have generated, and for each tuple, that is take the smallest tuple among this. For each tuple, just go past the repetitions of this tuple in the other blocks. Let me illustrate this with an example in the next slide, which makes it much more clearer. It is as simple as taking one tuple and then moving or rolling forward all other blocks so that they move past the present tuple that I have taken. That is, if they contain duplicate tuples. If they do not contain duplicate tuples, you do not have to move them. So and of course, once they are all moved, put the first tuple into the output buffer. Now this is possible, or this is possible to be done in an efficient fashion because the tuples are all sorted. That is, if a tuple t appears at one particular stage, then all tuples that are in some way greater than t should appear below them. Therefore, I just need to search each block until I find a tuple that is greater than t when I am trying to remove duplicates. This such a kind of merge elimination takes an order of m and b time, where m is the number of blocks in a sorted block set, that is one of the intermediate result block set that we have stored, and b is the number of tuples in a block, and n is the number of such block sets. If you remember merging algorithms, a merging algorithm between two lists of size m and n would take an order of m plus n time. Because we have n different lists of blocks of m different blocks, that is each list comprising of m blocks of data and each block containing of b tuples of data, we just multiply all three of them together so that we get the total time that it takes for eliminating duplicates from this. Let us look at duplicate elimination with an example that makes the process much more clearer. Now let us assume that as shown in the slide here, this is the first set of block set, that is first set of m blocks of data that is written, that is 1 2 is in the first block, 2 2 is in the second block, and 2 5 is in the third block. Now this whole thing is a set of 3 blocks that were written onto disk, and as you can see here, this entire thing is sorted. They are in sorted order, that is 1 is smaller than 2, less than or equal to 2, and so on until 5. This is the second set of blocks that were written onto disk, 2 3 4 4 4 5 and so on, and this is the third set of blocks that were written onto disk. We now start by taking just the first blocks of each block set into memory, and then considering just the first tuple in the first such block that was read. Okay. Now the first tuple says that it is or reads as 1. When I read 1 here, all I have to do to eliminate duplicates is to eliminate 1 from all other block sets. Okay. Now if 1 has to appear in all the other set of blocks, they have to appear at the top. They cannot appear somewhere at the bottom. This is because it is sorted in order. Okay. Therefore 1 has to appear in the top. So all we need to do is start from the top of each block set and start moving forward until we find a tuple which has a value or whose key value is greater than 1. So therefore, once we read 1 here, we look at the second block set and we read 2 to begin with, and we know that 1 does not exist in this block set. When we read the third block set, we read a 1 and cancel it out, read the next tuple, and this is also 1, we cancel it out, and then go on to the next tuple, which is a 2. So we know that we have exhausted all ones that have occurred in this block set, and we can stop this process here and output 1. So after 1 is output, the set of blocks becomes like this, that is 2 is at the front, all the ones have gone, and the block sets have been left shifted, so to say, in an appropriate fashion. Now the next tuple that needs to go out is 2. So you see that the first tuple here reads 2, and you have to eliminate all 2's from everywhere else. That is, return this 2 to the output buffer and start moving forward until you have eliminated all 2's. Okay? So therefore you cancel the next 3 2's here and end up at 5. In the second block you cancel the first 2 and end up at 3, and the same thing in the third block set as well, that is, you cancel the first 2 and end up at 3. This is depicted in the second slide, that is, after the second tuple is put into the output buffer, that is, after 2 is put into the output buffer, our sets of blocks looks as it is shown here, that is, all the 2's have been eliminated here and 5 has come to the top, and all 3's are that is, all 2's are eliminated here and 3 has come to the top, and all 2's are eliminated here and 3 has come to the top here. Now if I start to read 5 here, then there is a problem, because I have not read 3 as yet. 3 and 4 still exist before 5. Okay? So so I cannot start rolling this block set until I read until I go beyond 5. The simple answer to obviating this problem is to note that the first set of blocks from all the block sets are in memory. So we just choose the least element from the first set of blocks and then start rolling the blocks. Therefore we now choose 3 as the tuple to be output to the output buffer, and then start rolling each of the block beyond 3. Therefore 3 would be output from the second block set, and we will roll it until we find 4 here, and same thing 3 would be output here, and we will roll it until we find 5. That is, we roll the block set until we end up at 5, and so on. So in this way we can eliminate duplicates by taking the least element of the topmost set of buffers of each block set, and then rolling blocks until we move beyond the least element. How do we perform set union using sorting? Remember this kinds of algorithms that we looked at yesterday for relation at a time operators. We looked at duplicate elimination, we looked at different kinds of set union, theoretic operations like union, intersection, set difference, and so on. Okay? So set union is a binary operation. It is a relation at a time binary operator. Okay? And because it is a set union, that is, I have emphasized the word called set, it means that there are no duplicates in the result. As you might have imagined, the strategy for computing set union is very similar to duplicate elimination. When we have to compute the set union between two relations R and S, so let us say R union S, we just have to output all tuples from R and S without duplicates, as simple as that. Therefore the set union algorithm is quite similar to that of the previous algorithm, where you read blocks from R and S rather than just from a single relation, sort them and store them onto disk. Now it does not matter for us whether any given tuple that we have read belongs to R or to S. We can just consider R and S to be a single relation, and then start reading tuples from them, sort them and store them back to disk, and use the duplicate elimination merging technique that we just looked into in the previous example for eliminating duplicates. So, the output of this would be it is clear to see that the output of this would be R union S. What about set intersection using sort, using sorting techniques? Set intersection between two relations R and S essentially has to return the set of tuples that are common between R and S. This set intersection is slightly different from the previous two algorithms. Why is this so? This is because here we need to be concerned about, or we need to distinguish between tuples that belong to R and tuples that belong to S. In duplicate elimination as well as in union, all that we were concerned about is eliminating duplicates, that is, whenever there are duplicate tuples, you just return it once and then cancel out all others. But here you have to return tuples if and only if they appear in both relation R and relation S. Therefore, we need to have a mechanism of tagging each tuple as to where it belongs. Does it belong to relation R or does it belong to relation S? So, the simple strategy for a set intersection is shown in the slide here. Given two relations R and S, read them in terms of M blocks rather, and store the blocks on disk in sorted order. That is, read relations R and S and sort them and store them back on disk. Now, when reading it, ensure that the intermediate results of R are stored in a separate block set or in a separate buffer pool than the relations of S, so that we can easily distinguish between buffers that belong to R and buffers that belong to S. And in order to compute the common elements between R and S, we simply do the following. We take each block of R, that is from the block set, and take the first block in each block set and move them into memory, and read the smallest tuple. The first tuple in this means the smallest tuple in the block set that we have just read into memory, and try to roll S, that is try to roll relation S beyond this tuple, that is beyond the first tuple. If any that is if this tuple T existed in S, then there should be at least one block which gets rolled, that is, which gets left shifted. If there is at least one left shift in S, then it means that the tuple T is common between R and S. Therefore, it can be returned to the buffer pool or the output pool. If no such left shift happens in S, then the tuple T is not therein or is not present in S, and therefore can be discarded. And note that here we are assuming that R and S are sets, that is, there are no duplicates in R and S for this algorithm. If there are duplicates, then what we have to do is we first have to eliminate duplicates from R before shifting S, that is, take the smallest tuple from R, roll all other block lists in R until you eliminate duplicates of this tuple, and then start looking for occurrences of this tuple in relation S. The last algorithm that we will be looking at in the sorting strategy is the natural join function. The natural join, as you know, is an equijoin that operates on two relations. It's a binary operator, and it's an equijoin on attributes having the same name and domain that are in the two relations. So, assume that we have two relations R x comma y and S y comma z, where x and y, x, y and z are attribute lists, and where y is the common component between R and S, and assume that we are computing natural join between R and S. Now, a simple way of computing natural join is shown in this algorithm here. We first read blocks of R into memory. That is, we first read R in terms of m blocks and sort them on the y attribute now. We cannot sort them on the entire tuple contents. We have to sort them on the y attribute. This because this is the y attribute is the one that is common between R and S. Now sort them on the y attribute and store them back onto disk. And then secondly, read relation S block by block, that is m blocks by m blocks, and again sort it on the y attribute and store them back onto disk. Now what is it that we need to compute the natural join? Now for each relation or each tuple in R that is stored onto disk, we have to find all other tuples of S that are stored that are also stored onto disk that can be combined with this relation. Okay. Now we however encounter a small problem here. What is the problem? There could be situations where a given tuple in R can be joined with every tuple in S. Okay. Now if that is the case, especially if we are talking about outer joins where we can tolerate null values for y, then we may have to take a tuple from R and join it with every tuple in S, and we may not have of course we do not have enough memory to store every tuple of S in into memory and then start outputting it. So we have to do something else now. That is, there could be worst case conditions where even combining the intermediate results cannot be done in memory. That is, there isn't enough RAM to perform the intermediate operations. In order to tackle such issues, what we do is we start with the second level of what might be termed as external merging. What we do is, for each value of y that appears at the top of the first blocks of R, that is, read the first block from each block set of R into memory, take the value of y that appears in the first block of R, okay, and for each value of I that appears in the first block of R, note that here we cannot remove duplicates. We should have duplicates in the result, unless of course it is specified that there shouldn't be no duplicates. Okay, so for each value of I that are at the top of the first block of R, start rolling S, that is start reading the first blocks of S into memory and start rolling them and beyond until they go beyond the value of y, and take all these tuples and store them separately. That is, let us say you take tuple T1 from R and a set of tuples Ts from S and put all of them into another file. Okay. Now once you have put all of them into another file, you just start combining the tuple that you have found in R with each tuple that you have found in S. Okay. So of course, as you can imagine, this is a pretty this can be a pretty slow operation, because there are several amounts of disk accesses or disk writes that are happening here. The first set of disk writes are reading the first set of disk writes happen when we write the intermediate sorted relations back onto disk. The second set of disk accesses happen when we read each of the blocks from the block sets of R into memory, and then for each tuple we have to read each set of blocks in S, and for all matching tuples we have to write them onto some other intermediate file where they can be combined. Note that we cannot delete the tuples from S after we have done this operation, because there could be another tuple in R having the same value of y, which can also be joined with all these tuples in S. That is, for example, if we are joining, let us say employee and department, and let us say the join attribute is is the department number, that is for each department number attribute in the employee relation, find the department number attribute in the department relation and then join them together. Now there could be a case where 2 or more employees have are working in the same department and have the same department number. So when we have found the first employee with some department number, let us say D, and we have, assume that employee relation is R and the department relation is S. Once we have found the first employee who works in a given department D in S, we take the tuple D in S and write them onto disk so that they can be combined. However, this tuple cannot be deleted from S because there could be another employee who is also working in the same department and whose tuple also has to be combined with the tuple of the department. So therefore, natural join using sort is a slightly expensive technique. The next set of algorithms that we are going to see, or the next paradigm of algorithms that we are going to see, are the hash based algorithms. As the name suggests, hash based algorithms use a hash table at their underlying as their underlying data structure, and use hashing as the overall paradigm or the overall strategy on which the algorithms are based. The basic idea behind hash based algorithms are shown in this slide here. We first, given a relation R that is too big to fit in memory, of course, we read relation R block by block. We do not even have to read it m blocks at a time. If it is possible to read it m blocks at a time, fine, it makes it even more faster. Okay. Now after we read a relation R block by block, take each tuple in a block and hash it, move it through a hashing function so that it is hashed onto a bucket in a hash file. Note that what is remember what is a bucket in a hash file. A bucket is a set of buffers, is a chain of buffers that contain all tuples that are hashed to the same value for a given key. That is, all tuples having the same key would be hashed onto the same bucket. There could be tuples having different key being hashed onto the same bucket, which could well be possible, but what we can definitely say is that all tuples that have the same key will be hashed onto the same bucket. So all similar tuples should hash to the same bucket. Then we examine each bucket in isolation. We do not have to work across buckets anymore. In sort based techniques, note that we had to work across the buffer lists that were sorted buffer lists that were generated. In hash based technique, we can examine each bucket in isolation of the other buckets in order to produce the final result. So this slide is a reminder of what a hash file organization looks like. Given a tuple with a particular value key on which hashing is performed, the key then maps onto a set of buckets. This one shows static hashing, and of course there are also dynamic hashing techniques. Okay. So the hashing function hashes a key onto a bucket number. The bucket number in turn points to a chain of blocks that form the bucket, or where data or tuples that should line the bucket are stored. Let us quickly look at our usual algorithms for duplicate elimination and set theoretic operations like union, intersection, and so on, using hash based techniques. How can they be performed using hash based techniques? Let us first look at duplicate elimination using hash based techniques. This is quite simple, as shown in the slide here. Given a relation R which contains duplicate tuples, and of course which is too big to fit in memory, read the relation block by block, or m blocks by m blocks, and take each tuple in the blocks that are read and hash it to a set of buckets of a hash file. And let me reiterate the fact that if there are duplicate tuples in R, an important property that we have to note here is that because we are using the same hash function, if there are duplicate tuples, they will necessarily be hashed onto the same bucket. So we have already cornered in a sense all duplicates into the same bucket, and now our job is much simpler, that is visit each bucket and eliminate duplicates using either a one pass algorithm for duplicate elimination if the bucket can fit into memory. Remember how we did one pass algorithm for duplicate elimination, that is we have to maintain an internal hash or a internal index structure in memory and then eliminate all duplicates as and when we read the relation. So if the bucket can fit into memory, you can use an internal data structure or an in-memory data structure to eliminate duplicates, or if the bucket is too big to fit in memory, then we can consider this bucket as a relation, as a small relation, and use our previous algorithm, the two pass sort based algorithm for removing the duplicates in the buckets. What about set theoretic operations, union, intersection, set difference, and so on? For set theoretic operations involving two relations R and S, we maintain two separate hash files, okay, hash based file organization. Okay. However, these two hash files will use the same hash function, hash of k, and the buckets are also labeled analogously, that is bucket number 0 in the first hash file corresponds or is analogous to bucket number 0 in the second hash file, and so on. Okay. So if tuple t appears in some bucket n in the hash file of R, then if it is present in S, it should also appear in bucket number S of the hash file of S. Okay. And in addition to that, the standard property that all duplicate tuples are always hashed to the same bucket in a given hash file. So using this, it is quite simple to perform set theoretic operations using hash based techniques. For example, if we have to perform union, all we have to do is hash each tuple of R into R's hash file, and hash each tuple of S into S's hash file, and take each corresponding buckets, that is bucket 0 of R and bucket 0 of S, and eliminate duplicates and then output the results. Similarly, if we want to perform intersection, we just examine corresponding buckets, bucket 0 of R and bucket 0 of S, that is bucket I of R and bucket I of S, and then return only the common elements. And the same thing for set difference. So that is quite straightforward. The last technique in hashing that we are going to see is what is called as the hash join algorithm. This is perhaps the most widely used technique for performing natural joins because of its simplicity and efficiency. Natural join over, let us compute natural join over relations R of x comma y and y, s of y comma z, where y is the common component between R and S. Now all tuples, now we are going to first read R and S and use the y component as the key to perform the hashing rather than the entire tuple. Now all tuples having the same value of the y component should hash onto the same bucket, right, if we are using the same hash function. Okay. So if the same hash function is used for R and S, we just take the corresponding buckets, that is just take bucket number 0 of R's hash file, and for all the tuples that you find, if they can be combined or if they can be joined with any tuple, then this tuple has to necessarily exist in bucket number 0 of the S's hash file, and so on. So given this property, we can it is enough for us to examine just the corresponding buckets in order to perform the join operation. This makes the join operation extremely efficient because we do not have to perform too much of lookups when we are performing the we do not have to do too many lookups when we are performing the join. Such an algorithm is also called the partition hash join algorithm, because the pure hash join algorithm is a slightly different algorithm from this, but this is a widely used algorithm for computing natural joins in many DBMS systems. So let us summarize what we have learned today in the 2-pass algorithms. So, let us summarize query processing in general and then go back to the 2-pass algorithms that we have studied today. We looked at the different stages of query execution to begin with, and then we saw that there are 2 stages, namely that of the logical query execution plan and the physical query execution plan that are especially of interest. And then we saw what are some of the language constructs that make up the physical query execution plans, and then we looked into algorithms that can be built to perform these internal queries or physical to answer these physical queries using these physical query execution plan constructs. And these algorithms could be either single pass algorithms if the which can be used if the relations are small enough, or if the query is a tuple at a time query, and there are multi-pass algorithms which can be used if the relations are big. Among multi-pass algorithms, or rather in 2-pass algorithms, we looked at sort based algorithms or sorting based strategies for performing several of these operations, and hash based strategies for performing several of these operations. We have not looked at index based strategies, which is quite analogous to sorting and hash based strategies. We shall briefly visit index based strategies in the next session before we take up the logical query execution plans and ways by which queries can be optimized. So that brings us to the end of this session. Thank you.